Welcome back to my channel. Today I have a very special thing to introduce. I have a new series called What the Average Human Needs to Know About Astronomy, Elise edition. So this is my little crash course, should we say, on all different astronomy topics. And today I'm going to start with the solar system. So what the average human needs to know, about the solar system. And this stemmed because, if I may give you my credentials, I have been studying astronomy for years. This is like over a decade I've been studying this. I've taken multiple college classes on chemistry and physics. I'm currently taking a class at UC Berkeley on astronomy. I have taken multiple camps, classes, courses, different sorts of things on astronomy. I love it so much. It's my passion project. My boyfriend and I do it together, so don't worry, I am pretty well qualified to teach basic astronomy concepts. And so today we're going to debunk a bunch of myths and go into what really is in the solar system that we see when we look up into the night sky. And we'll be going through all of this throughout multiple sessions, so this is just the first one. So if you don't mind me yapping, let's get into it. The first thing I want to talk about is scale. So whenever we talk about the solar system or anything in the universe, normally when we see pictures on the internet, they're not usually to scale. So those objects appear a lot fainter and smaller, or a lot closer and bigger than we actually see on photographs. And sometimes that scale is hard to get our heads around, because normally when we say that 2 football fields length away is a scale, we can kind of plot all the different things along that scale and make it bigger or smaller. But as we get towards the size of a city or a country or a planet, or even multiple distances away from planets, that's super hard for our human brains to wrap around, because we're not tactically familiar with any of that. And so sometimes scaling is hard to teach. And so instead, we're going to assume not everything that I'm going to show you is to scale. So the first thing that I made to help us kind of get an introduction, kind of like a table of contents of what I'm going to be talking about today, is this little card right here. So this card is fun. I'll just put this in your view. But this is kind of like a little model on paper, a little 2D paper of what our solar system consists of. So to go over it very, very briefly, we've got the sun right here. We see it when we look up into the sky every day, unless, of course, fog. And then we've got Mercury, Venus, Earth, Mars, a thing called the asteroid belt, Jupiter and its Galilean moons. There are 4 Galilean moons. Then we've got Saturn and its 2 famous moons, Uranus, Neptune, Pluto, which is not actually a planet. And then we've got a thing called the Kuiper Belt, and I will be talking about something inside of it called Eris, and then something called the Oort Cloud on the very far reaches of our solar system. And so this is the general model I'll be talking about, and I'll be referencing this throughout the video, but we're going to start off today with talking about the sun. So key point before I say anything else is the sun is actually a star. And this might be obvious to some of you, but some of you might be like, the sun is a star? Really? Yes, it is actually a star. The sun is the same type of star that we see when we look into the night sky. It's got a giant mass, lots of brightness. That is, in fact, a star. And what makes this a star and what differentiates a star from a planet is not necessarily the mass, although that is pretty important, but it's also the composition of the star and what is happening inside the star in the core. So the sun is a star because it is composed of mostly hydrogen and a little bit of helium. I think it's 1 or 2% helium, but it's mostly hydrogen. And that hydrogen is in a gaseous form. Actually, it's not really mostly gas. It's kind of more complicated, and you can do a deep dive into this, but for our purposes today, we'll say it's made of gas. But the sun is really made of plasma, which is basically like a subatomic soup of charged particles, which is kind of hard to wrap your brain around, so we'll say it's gas. It's gas with electric charge, and it's mostly hydrogen. And, in fact, there are 700 million tons of hydrogen that are converted into 695 million tons of helium every second. And those 5 extra million tons are what is used to power the core of the sun through something called fusion, which is basically where the pressure gets so great because there's so much mass in the sun, there's so much hydrogen in that sun that's compressing each other, and the pressure as you get closer and closer is greater and greater and greater, and eventually those hydrogen atoms congeal together to make a helium atom. And so that is what fusion is. It's taking 2 different atoms and fusing them together, not fission, fusion. Fusion is what happens in the cores of stars. And on our planets, that does not happen. We normally have, for instance, in Earth, an iron core, and as we'll learn later, there are different types of cores that different planets and moons can have, but there is no fusion that happens in the core of that. And what fusion does is it produces energy. And so by fusing those hydrogen atoms, we produce helium. We produce energy from that helium fusion, and that 5 extra million tons is what is used every second. 5 million tons every second. It's a crazy number, I know. That is what is used to power our star and what gives us that light and that heat, because as Einstein's famous equation said, E equals mc squared, we know that energy can be produced by that mass. So that is what is used to power the sun. And then we travel out a little bit, we go a couple, million kilometers away, and we get to Mercury. Mercury is a very interesting planet. It's a very tiny planet, and it is mostly made of rock. It is very hot and very cold because Mercury is super close to the sun. It whips around the sun very, very quickly and has an orbital period of just 88 days. So it whips around like pew, 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 and goes super fast. And so Mercury is interesting because it's got I believe it goes around once every, I believe it's 59 days. It stays 59 days, but it goes around 88 days for sure. And it gets a lot of heat and a lot of energy, and also because it's so close to the sun, it is very heavily cratered. So Mercury is very, very tiny and very heavily cratered. And Mercury is a great object to study, but the problem is because it is so close to the sun that when you see the sun rise and set every day, Mercury is along that same path. So when the sun is setting and the sky is getting dark and we're able to see those planets, Mercury is also setting at the same time. And this is super, super hard to study because we've got all that muck and fog and all that sort of stuff on the horizon that's dimming our view of the stars and dimming our view of the planets. And that's really hard to study objects on the horizon there where Mercury and the sun are, because they're already setting, and it's setting right in the middle of all that smog. So it's kind of hard for us to study Mercury on Earth, but we can study them far away. Now we're moving on. We've got the sun and Mercury. We're going on to Venus. And Venus is a cool planet because it's in what we call the habitable zone of our solar system. And the habitable zone is kind of a finicky term because technically speaking, Venus, as we think about it, Venus is a boiling hot planet close to the sun. It's not necessarily habitable, but it is within that habitable zone where it's just far enough away from the parent star that it could host life hypothetically. In real life, we see that that's not really the case, but technically it could. So Venus is a cool planet because it is close to the size of Earth. It's close to the mass of Earth, and it is close to the physical volume of Earth. So it looks similar. When we compare Venus and Earth side by side, actually the difference is very, very small. It's under 10% different in terms of mass and volume. But Venus is cool because it's super boiling hot. It's got this really, really thick atmosphere that reflects most of the sunlight that hits it. So when we see Venus, we see it as this super, super bright, it looks like a star, and it used to be thought of as a star, but it's a bright planet. And this is super interesting because it makes the interior of Venus pretty hard to study because we just see that light reflecting off of it all the time. And what's so cool is if this is the sun and this is Venus orbiting around the sun like this, it's got 263 days where it's going to come over the sun and we can see it. And then while it passes in front of the sun, if you're Earth, it's passing in front of the sun. We can't see Venus because the sun is blocking it out. And then it comes back around and it goes around again. And then there's a period of 50 days this is 8 days and this is 50 days, because it's so far away that the area it travels is smaller compared to where it's bigger right in front of Earth. So we call one side the morning star, whereas the sun rises because Venus is closer to the sun than we are. Then we can see it along the sun's path, and it's called the morning star and the evening star in those 263-day periods. I would also like to mention that if you do the math and you're like, wait, but 263 days plus 263 days plus 50 plus 8, doesn't that mean that Venus's orbit around the sun is more than Earth's, which is 365 days? That doesn't make sense. Shouldn't it be going around faster? And the thing is, we measure that. There's two different types of days. There's a solar day and there's a sidereal day. And the difference between those I will get into a little bit later. But a solar day is relative to the sun, and a sidereal day is relative to the stars. So Earth's sidereal day is 365, we'll get into that later, days. And then Mercury's and Venus's are shorter. But we know that in order to have that kind of like 263, it needs to be that Earth and Venus are aligned. And so that actually happens closer to 500 days rather than 365 days. So that is Venus. Now we have our home planet, Earth, and we have a moon. And I'll get into the Earth and moon and sun and their cycles a little bit more, but it's our home planet. It's composed of mostly water. There's only a little bit of land. We have tectonic plates. Inside we have a crust, a mantle. There's an upper and a lower mantle, and our core. And our core is mostly iron. And so that's why we have a giant magnetic field, which is why when the sun shoots fun stuff at us, we see auroras in the northern and southern pole, because that is an effect of something we call the magnetic field of Earth. It draws in those charged particles and makes fun colors out of them based on something we call spectra. And I will get into spectra later, so I'm sure you have a bunch of questions, but I'll get into that later. So, Earth and the moon. And the moon is obviously a moon of Earth, so it goes around Earth once every about 27 days. And then we have Mars, and Mars is a fun planet. And a lot of people ask me, like, well, Elise, why is it red? And the reason it's red is it's actually a chemical effect called oxidation, where it basically rusts over. So if you've ever seen like a rusty car on the side of the road that has been there for a long time and it looks red, it's because of rust. So basically, Mars is mostly basalt, which is a type of rock underneath, but it also has a property in its rock that makes it oxidize and turn red, because Mars has a very, very thin atmosphere. And so that is why we get that red oxidation, because that oxygen is interacting with it's oxidizing. It's oxidizing. So that is why Mars's crust is red. And then I have more to talk about with all of these, but we're getting into the asteroid belt. And the asteroid belt, some people thought it was a failed planet that may have broken apart and kind of like scattered around. But basically, it's got this like thin disk between Mars and Jupiter of a bunch of different irregularly shaped rocks and chunks of ice. So it's far enough away that it can get ice and rock. So it's got like a bunch of different types of things there, but it spans pretty far out, and we get some of our short period comets. I'll be talking about comets from the asteroid belt, and also from something called the Kuiper Belt. Some short period comets from the Kuiper Belt will come in and kind of like zoom past some of the gas giant planets, which include Jupiter, Saturn, Uranus, Neptune, and their gravity is so big it will funnel them into the asteroid belt. So that's one thing that can happen rarely. And then we get into something called Jupiter. Most of you have probably heard of Jupiter if you learned that in school. Jupiter is one of the biggest planets. It's mostly gas or liquid gas. Liquid like hydrogen and methane is some of the primary components of Jupiter. Jupiter is about 100 times the size of Earth. So about 100 Earths can fit in Jupiter, and about 1,000 Jupiters can fit in the sun, I believe. Or it might be the other way around. I have to fact check that. I will put it up at some point in the description, maybe, if what's different. So, yeah. And then it has 4 Galilean moons because Galileo Galilei discovered 4 moons orbiting around Jupiter in frequent cycles. And what's so cool about one of them, Ganymede, which I'll talk about first, is it's actually in between the size of Mercury and Mars. So Ganymede's pretty cool. It has its own core. We think it has its own magnetic field. We think it has its own like little liquid water layer inside of it underneath the crust, kind of like a mantle-ish kind of thing. And so that's really cool. So that's the first one, Ganymede. And then we've got Io, and Io is the closest to Jupiter. And Io is basically a volcanic planet. So it's constantly erupting, lots of volcanic activity. It's got fun colors. It's got like brown and green and red and all of these different colors because the volcanic activity shoots sulfur up and then it comes onto the surface and makes fun colors. And then we've got Europa, and Europa is a particular moon of interest right now because we think that it has this moving ice crust. So when we get earthquakes, it's basically our tectonic plates which lie under the crust pushing up on each other. And around Europa, we think that the same thing is happening with ice because the mantle of Earth moves the crust over each other and basically slides them together. And that's what makes like little dips and ducks and mountains and volcanoes and all that. But on Europa, we think that there's a layer of liquid water or some liquid underneath an icy crust. Because when we took images of Europa, we just saw thin little streaks. We never saw any craters. So if there was any impact on Europa, it had to be covered up somehow, kind of like how lava reshapes the landscape. We thought there was something with ice pushing it up. And so we're going to do this thing called Europa Clipper, which I would highly recommend you check out by NASA, where basically we're going to go to Europa and do some sampling there and figure out really what is Europa and could it host life? Is there that liquid ocean under and what's going on? So that's a really cool thing to check out. And I've mentioned the 3 moons that interact most with each other, which are Ganymede, Io, and Europa. But there's another one, and this is maybe the least talked about one, and it's called Callisto. And Callisto is a really interesting planet because it's mostly rock, and it's mostly craters, and there aren't many fun things about Callisto that I would have to say, except it's the farthest away and doesn't interact as much as Io and Ganymede and Europa do. So it's kind of like the weird 4th Galilean moon that's farther away. But yeah, that's Jupiter. And so we go on to the second gas giant here, which is Saturn. And it's got 2 main moons, but the close one is Titan. And Titan, there's so much I can talk about with Titan, so I'll do it in another kind of episode. But Saturn's cool thing, as you think about Saturn, you think about rings. You think about the fun, big rings. And as Galileo was looking at that with his telescope, he thought that they looked like ears. Because if my head is Saturn, and we're looking at it straight on, if these are the rings that wrap around my head, if I'm looking at it flat on, it's going to be like a thin disc. And those rings are blocked out by the brightness of the planet until here. And then they spread out like this, like ears. So he couldn't see that the rings fully wrapped around Saturn. He just saw these like ear-looking things. And so he said, oh, they look like ears, but they're not, they're rings. The cool thing about those rings is they are only 10 meters thick. They're only 10 meters thick. So if you scale down Saturn to the size of a piece of paper thinness, those rings would be less than 1,000 times thinner than that paper in comparison. They are so small. And they have different layers. So inside of the rings, they have the A ring, the B ring, the C ring. And what's so interesting is, I'll go into all this later, but the F ring is actually the furthest one. And the C ring is one of the closest ones. And then it goes F ring, then A ring, then B ring, then C ring. It's really weird, but astronomers are very original and name them like that. So Saturn's super cool. Also, another thing that's cool, another fun fact, if you will, is that at the North Pole of Saturn, we see a hexagonal looking shape. And that's so weird. You think, why is there a hexagonal looking shape on Saturn? And it's due to fluid dynamics, fluid motion. And I'll talk about how and why that happens. And it has to do with its location and fluid dynamics. So I'll get into all that. But that's something most people don't know. And now you know it. Okay, so we're migrating a little bit further out, Jupiter, Saturn, and this is where it ends I just made this little line here because it ends where we can see with our naked eye. We need a telescope after that to look at any of these other objects, and the first one is Uranus. And not Uranus, no, please say Uranus. Uranus actually technically spins, I believe it's 89 degrees, or it's 98 degrees. I will put it down which one it is, I forget. But it spins on its side almost. So its rings has a very, very faint set of rings, look like they're vertical, which is super cool. It spins kind of like this, which is really fun because Earth has about a 23-degree tilt, just about a 23-degree tilt, but Uranus has it all the way on its side, so it's spinning like that. So as it's going around Earth, it's spinning like this instead of spinning like this, which is really cool. And also this is a great time to say we have a heliocentric model, and all of the planets are almost perfect spheres. They are spheres. They are not flat. They are not bowls. They are not crescent moons. No. They are spheres. They are 3D spheres that go around the sun in near perfect circles. Some of them are more elliptical than others. Ours is only a 3% ellipse. But just to put that out there, the sun is the center of our solar system, and we are going around the sun. So just a good time to put that out there. So next one, if we got a bit further, is Neptune. And Neptune is the last planet. So it's not Pluto. Pluto got debunked in 2007. It's a dwarf planet. It's no longer a real planet with the others. So sorry, Pluto. For any of those who say Pluto is a planet, there are reasons why, and I'll explain that in another video, but it is not, in fact, a planet. So, yes. But Neptune is the last planet, and Neptune's really cool because it's super, super far away. Its orbital period is very, very long, and it's super, super icy. And Neptune wasn't actually discovered until quite a while afterwards because it's so far away and so hard to detect. And Neptune took some funky observations to detect it, actually. But just as I forgot to say, Jupiter does have a great red spot. Most of you probably knew that. It has a great red storm, a cyclone. I'll get into that later. But Neptune also has those cyclones. It has a pale blue spot, which is like, it's not exactly the same size as Jupiter because Jupiter is enormous, but it does have cyclones, or those storms, which are basically like gaseous hurricanes. I can put it like that. And then we go out a little bit further, and we get to Pluto. And Pluto is a dwarf planet. And for a long time, people didn't understand what they were looking at when they looked at Pluto because it's so reflective. It's so metallic. It's so shiny. People were like, what is on the surface of Pluto that's making it so reflective? And it's actually some mineral tracings in the planet's surface that makes it so reflective. And it's still really reflective when you try to look at it through a telescope. It's like, whoa, that is very shiny. And so that's Pluto. And Pluto has a very odd orbit, which is why it was debunked as a planet. So I'll get into that and why it is not actually a planet. I'm sorry. And then we travel quite a bit further out and we get to this cool thing called the Kuiper Belt. And I'm sure you've heard of the asteroid belt, or some of you have heard of the asteroid belt, but not all of you have heard of the Kuiper Belt. And the Kuiper Belt is named after, I forget his exact name, but his last name is Kuiper, And he discovered the asteroid belt, which is a cool, it is like the asteroid belt, but it's much broader, and it contains a lot colder objects and a lot of things called long distance comets, long period comets that come and zip by the sun or by a planet and then take a really long time to come back around and do that again, like Halley's Comet, for instance. You might have heard of Halley's Comet. That is a long period comet that will zip around and come back. So that's an instance of what an object is in the Kuiper Belt. But there's another cool object that's like, it's not a planet, it's like a mini moon. It's a spherical object. It's called Eris. And Eris is really fun. I'll do a whole lesson on Eris, but keep in mind Eris is a fun thing to Google and check out. And then we reach the very edge of the universe. Sorry, not edge of the universe. I'm very tired. Edge of the solar system. This is not the edge of the universe. The universe is huge. But it's called the Oort Cloud. And the Oort Cloud extends for a very, very long time. And we actually don't have a lot of evidence that it exists, but we do have research that points us to what possibly could be the Oort Cloud, and it makes a lot of sense for it to be there. And so we think that there's something called the Oort Cloud out there. And again, there is a scientist that I forget, his last name is Oort, but he discovered the Oort Cloud. And the Oort Cloud is basically a collection of ice and dust particles that we think is like a sphere around our solar system. And there are probably like thousands upon thousands upon thousands upon thousands upon thousands of objects out there that are mostly particles. Because actually the sun contains 1% of all the mass in the solar system. It contains 99% of all the mass in the solar system. I'm sorry, why am I so tired? It contains 99% of all the mass in the solar system, which, if you think about it, is a lot of empty space. And 0.9% is Jupiter. So 0.9% of the remaining, no, I'm right. Anyway, I'm so sorry, I'm so tired. The point is that there's a lot of empty space and the sun contains a lot of that mass. So it's a mostly empty space. But the Oort Cloud surrounds that, and I'm getting really tired. But that was my mini introduction lecture. I'd probably do a better job of this if I was more awake, but I'm not. So I hope you enjoyed, and I will be talking a little bit more about that. I'm really good at talking about the physics of things, so I will talk more about physics, and my specialty is I like something called radio astronomy, which is basically using fun radio waves to detect chemical compositions of things very far away. So figuring out an organic molecule. Does it live in a starless core? Does it live in a nebulae? What do we know about this molecule? How does it interact with the particles in space? What does it mean if this is composed of this and this, and what can we predict? And it's super cool. I highly recommend looking at radio astronomy because it's fun. So that's my specialty, less the solar system, but I know some things about it. So I will talk to you more later, and yeah.